I am Matt Paden. I'm the current president of ELSO and would like to take the opportunity to welcome you all to the 33rd annual ELSO conference. I've got to tell you, I just am very excited about the conference that we've got put on today. To see all of us here back in the same room again is just, I can't tell you how much that means to me. And seeing old friends, and then seeing many of you who are here at the conference for the first time. So if you don't mind, if you're here for the first time at an ELSO conference, would you raise your hand? Exactly. And so, you know, when we've looked at this, this is exactly what we know we need. ECMO is growing and growing like never before. And this is a place where we can all come together and learn. And so I first want to start by thanking all of the ELSO staff who put together this amazing conference. And they are here to help you throughout your time here. If you need anything, please go to the registration desk and ask. I'd also like to thank Kara, who has done an absolutely incredible job being the chair of the conference and has put together just an amazing scientific program for us today. With that being said, I want to welcome you all, and we'll hand it off to Kara.
Thank you so much, Matt, and thanks everyone for being here. I just want to echo what Matt said and welcome you all to the 33rd Annual ELSO Conference. I mean, I'm so thrilled to be together in person again in Boston, and really want to thank all of our attendees, old and new, familiar faces and new ones, our exhibitors, our speakers, and moderators for making the trip really from around the world to Boston today. You know, the global nature of ELSO is really one of its greatest strengths and is really unique in medical societies. And truly, we have a world's body of ECMO knowledge amassed in this room. And I'm so thankful that we were able to put together such an exciting program for all of you. So I hope you have the next few days to learn from each other, to connect with colleagues old and new, and to really enjoy being back together again in person. I will now turn it over to our President-elect, Dan Brody, and the introduction of our keynote speaker.
Thanks, Dan. So I had planned to welcome everybody and thank everybody, but I guess that's been done. But I'm going to do it anyway, because it is truly a pleasure to be here in person with all of you. I mean, like in a way that I think you can feel the excitement in the room, and everybody who comes up to us says the same thing. It is just so great to see you in person. And for those who will eventually watch this on video, I think it's going to be a terrific conference, and we welcome that, and hopefully you'll be able to get to the next ELSO meetings. So I also want to offer some thanks just to start, because I think it's so important to recognize everybody. First and foremost, Kara and the entire conference committee for putting together, if you looked at this program, holy cow. It's over 200 speakers from all around the world, representing folks who are new in the field and those who've been doing it for a long time. And I think you will really enjoy the quality of the program. I would be remiss not to thank the ELSO office because none of this, not the conference nor ELSO, would be possible without them. And that's everybody. That's Kenny and Alex and Peter and Christine, Elaine, Phil, and Joanne, who also really helped with the conference. So thank you all very much. It's a tremendous effort to make all this happen. And I want to thank Bob, Dr. Bartlett, and Wanda, without whom none of us would be here. I know that's not the traditional greeting, but that is absolutely true. And finally, I want to thank the person who never gets thanked, Matt, who is our president and has had what could be called a very difficult presidency, having navigated through two of what were historically the most difficult years that we've all faced, and certainly that was true for ELSO as well. And he did so with a deft hand and a fair amount of wisdom. And it's been a true pleasure to work with him and with the rest of the ELSO board. So I want to thank them and the ELSO staff and Kara and the conference committee. And then, of course, it is my great honor to introduce our keynote speaker today. The speaker is Dr. Derek Angus, and I think Most people in the room are probably quite familiar with him. There may be a few who are not. I think this is going to be an absolutely terrific talk. By way of introduction, Derek is a distinguished professor and the chair of the Department of Critical Care Medicine, as well as an associate vice chancellor for healthcare innovation at the University of Pittsburgh Medical Center. You may also know him as one of the senior editors for JAMA, where at that perch, he is able to impact all of us in the way that we understand and absorb modern medicine. If you don't already know him, he is truly a luminary in modern critical care, as well as a thought leader in healthcare today. So finally, I would say that Derek is a masterful storyteller and a captivating speaker, and you are in for a treat today. So without further ado, I'd like to welcome Derek to the podium. Thank you.
I was just going to say, oh lordy, and sure enough, Dan said, you're going to have to live up to that. So thank you very much for inviting me. It really is a privilege. I feel flattered. I'm not an ECMO researcher, and it's been a number of years since I gave up my ECMO privileges. But I'm a big fan of ECMO. I can still remember very clearly over 20 years ago in the cardiothoracic ICU at Pitt, I had a patient about 60 years old who at the time I thought was old, who'd had a heart transplant, and he was in the ICU because he was breathless, and he was breathless because we'd found out that morning he had acute cellular rejection. We'd just got the biopsy back. And I'd started him on a gram of Solumedrol, and I'd cranked up his immunosuppressants, and I'd carried on rounding, and he arrested. And it was a witnessed arrest, and we were doing good CPR, but we were 30 minutes in, and I was getting nowhere with his rhythm, nowhere with his heart, and the head nurse looked at me to sort of say, we're going to call the code. And I sort of said out loud, or could we just emergently cannulate him and put him on ECMO? Because I was thinking, he's had like 30 minutes of the Solumedrol. There's no way his ACR is fixed. And thankfully, not everyone thought I was crazy, and we literally cannulated him on the spot. And 5 days later, he was off ECMO, he was off the vent, and we were writing his ICU discharge orders, and he was neurologically intact. ECMO is breath that we can give to other humans when that breath would otherwise have been extinguished. It really is, it's a remarkable feat of modern medicine. And we have it in modern medicine's toolbox because of this community. So really, it is an honor to come here and talk to you about ECMO. Now, I'm not going to talk about all of ECMO. I'm going to talk about ECMO in one particular space, ECMO for acute respiratory failure, and particularly acute respiratory failure for adults. And I'm going to do that in part because that's all a lot of you have been doing. We've all been having virtual meetings while ECMO programs all over the world have absolutely been on the front lines taking care of COVID patients with COVID-induced ARDS. And again, I want to really thank you for that. And particularly, if you don't mind, I will shamelessly do a call out for our own team in Pittsburgh who put over 200 COVID-induced ARDS patients on VV ECMO in the last couple of years. And so this is our team, and thank you very much. And that's a segue to say, it didn't just begin with COVID. Over the last decade or so, sort of almost out of nowhere, we started doing tons of ECMO in adults, as you can see in the dotted line here. And if you go and look on the ELSO registry, you can see the #1 reason for that is ARDS. The #1 indication worldwide over the last 5 years for ECMO has been adult acute respiratory failure. So let's talk about that. Because there's definitely a little bit of controversy. We're going to start the talk with the pop quiz. Anyone know who this is? Okay, so it's not fair. This is a medical conference, and this guy up here is Ludwig Mies van der Rohe. The reason I put an architect on the screen is because this person is arguably the biggest big vision thinker anyone has seen in the last 200 or 300 years. He was the father of the Bauhaus movement, and he essentially ushered in modernism. And if you walk through Boston today, if it hadn't been for him, all the buildings would still look like it was the 19th century. He is the father of sleek lines and modernism. He, arguably more than any other human, has changed the shape of the human world as we see it. And yet, at the same time, his most famous phrase is, "God is in the details." The pesky, irritating legacy that Mies van der Rohe left us with is if you want to create meaningful, sustained change, you have to simultaneously do both the big picture and the small details. It would be much nicer to only do one or the other. I'm just a big picture guy. Someone else takes care of the details. I'm going to sweat the details, let someone else work out about the big picture. Well, actually, you kind of have to do both. Pop quiz number 2. This is an easier one. Does anyone know who this is? So this is Peter Safar, or Peter Safar. So Peter Safar was my old mentor, and he's very famous for inventing mouth-to-mouth and being one of the fathers of CPR. And he was one of the first presidents of the Society of Critical Care Medicine. And when he was stepping down as the president of Critical Care Medicine back in 1974, he wrote a 2-page letter, a missive, a set of instructions really, to the critical care community. It was entitled Critical Care Medicine Quo Vadis. Now he could have said, Critical Care Medicine, whither goest thou, or where are you going? But you know, he's European, so he had to throw in a little Latin. That was a joke. Okay. And he was totally channeling Mies van der Rohe. He laid out a very detailed set of instructions around details for intensivists, a sort of an RFA for specific research questions, organ by organ, that all had to be answered. And then at the same time, without losing breath, he said, and you also need to solve critical illness at the population or the public health level. You should not confine critical care to the ICU. You should not think that critical care job is just taking care of the patient in front of you, but you should take responsibility for the whole system of care necessary to ensure the best possible outcomes for all the patients who develop critical illness. Okay, so as children, we see furthest when we stand on the shoulders of giants. So I will shamelessly channel this sort of van der Rohe Safar ethos and try to give a talk about where are we going with ECMO for acute respiratory failure, and suggest that it's not just about getting the details right around optimizing the device or the details around optimizing team and protocols, but we have to think through the entire distribution of care across all of the region, in this case Massachusetts, to optimize triage across the entire at-risk population and own all of the problem. And so in so doing, then, we need to move along simultaneously in addressing all these interrelated questions, like what are we really offering when we say ECMO? Does ECMO actually work for ARDS or acute respiratory failure? If yes, in whom? If yes, how should it be deployed? If we're not sure, how are we going to settle the issue and find out? Okay, so at this point, I've set up that the #1 reason for doing ECMO is adults with ARDS. And I'm now suggesting maybe we're not sure if it works, and I'm telling that to all of you who are all doing ECMO and ARDS. So in order to sort of prevent you from throwing tomatoes at me, et cetera, let's just stop for a moment and just walk through the counterfactual on why would ECMO not help. Someone who's sitting there with terrible gas exchange, looks like they're about to die, and ECMO can totally fix the gas exchange. But there are 3 big reasons why that might still not be enough, of course. First of all, even if you didn't put them on ECMO, modern conventional ventilation, especially in the hand of an expert, may do enough to squeak by. Gas exchange might not be what kills you. There may be another organ system that's going to take you down with another problem, or the delivery of ECMO itself may come along with lethal complications. So how do we line up the evidence to support ECMO for ARDS? And it essentially comes in 2 buckets. One is a huge bucket, a bucket of lots and lots of case series, which I cannot possibly review. I cite here only the latest, which is a complete tour de force and actually comes from ELSO. And the other is maybe a slightly stronger causal instrument for truly measuring cause-effect, a randomized trial. And although I'm totally happy to be told that I've missed one, as best as I can tell, there are essentially 4 classic trials of ECMO in adult ARDS, and we'll talk about them. So let's just start with the case series just for a second. There's an unbelievable paper from ELSO in Lancet about 18 months ago that just shows off the power of the ELSO registry. The detail with which you can describe what happened to the patients on ECMO is fantastic. And yet, in the same issue of the Lancet, the current director of the British ECMO program wrote the accompanying editorial, yeah, you can read this report, but we still don't know if they needed the ECMO. We don't know who didn't get the ECMO. And it's still the, can you believe he wrote this, the conundrum to clarify before we decide if ECMO is worth using or not. It's like you're asking this now, sort of 2 years into the epidemic, and you're still like raising the question of whether you should be doing ECMO. And it feels like deja vu. Because the last time we had a big epidemic with H1N1, the Northern Hemisphere was all worried about H1N1 spreading through the Southern Hemisphere and rushed to publish these early series on what was happening down under. And so a paper ran in the New England, and in commenting on it, Dick Wenzel and Mike Edmund said, very nice paper, but by the way, we have no idea if the ECMO actually helped. A week earlier, there'd been a real drill down, an ELSO-like drill down on the exact sort of course of ECMO on patients in Australia and New Zealand. And that one also had a near identical editorial saying, will the use of ECMO actually decrease mortality? Now, this one you should take with a pinch of salt because I'm not sure I trust the authors of that editorial. But let's just put these historical series in a bottle for a moment, put the cork in the bottle and put it back on the shelf. Because I would put it to you that you just can't tell from these observational series. And let's turn to the trials. I'm sorry, I couldn't resist. We're coming to Massachusetts. There's 4 trials. You can probably tell. I'm not suggesting that ECMO went through the same trials as the Salem witches, or maybe I am. Trial number 1. I just want to stop for a moment and say that I want to offer my condolences to anyone who knew this gentleman, because this is Warren Zapal. And Warren Zapal died last year after a long career predominantly spent in Boston, not far from here, and was a true giant in the field. It would take the rest of the week to list his accomplishments. But in particular, in ECMO, he did a couple of huge things. First of all, he led some of the most important large animal studies of ECMO prototypes in the 1960s in an animal lab at the NIH. And then, when we started putting, I say we, I was like 10 years old, when we, the community, started putting ECMO into adults with ARDS, he got NIH funding and pulled together a number of luminaries, including Professor Bartlett and Dr. Hill and others, and brought all the current ECMO centers in the United States into a room to do the first randomized trial. This is a remarkable trial. 150 patients on the planet, adults, had had ECMO at this point. And he said, enough. We can't go further. The world needs to know if this works. And they started, and although the trial was published in '79, he was getting this protocol written in '74. This was like 18 to 24 months after the first patient. They were saying, stop already, and let's sort this out for everyone at the public health level. He was thinking big as well as focusing on details. They thought we should do pure severe ARDS, so we're not going to put in patients that got terrible trauma because other things could kill them. So we'll have quite tight entry criteria. And they also already knew about trying to control all the rest, protocolizing the rest of care and having a common approach. Although I should say, it was 1970s critical care, which is a bit eye-watering. I'm going to show my age here, but for example, fluid overload was defined as a wedge higher than 26. Who knows what a wedge is? Okay. If you do remember what a wedge is, you probably remember 26 is way north of wet. Okay. They enrolled 90 patients at 9 centers over 4 or 5 years. That's 1 patient every 6 months. So it was definitely hard to recruit. And in the ECMO arm, they were giving 2 liters of blood products a day, not through choice. It was a slog, and it was horrible. It was horrible. Everyone died. And so they ended up writing, ECMO doesn't improve survival. ECMO doesn't even help speed lung recovery. The device is not fit for purpose. And so there's just no clinical role for ECMO in ARDS. This is from a group of researchers, including Bob, who had sunk 10 or 15 years of their life into ECMO. And then they'd done this trial, and the results were devastating. And with clear-eyed vision, wrote in an incredibly transparent way about how you can't do this. It's not ready, it's not right. It's actually an amazing piece of science. And it worked. It totally shut everything down, and we had crickets for 15 years. The device was getting better, and it was being used in neonates, but no one was using it in adults. It had been stopped. And then, one of the groups, LDS Hospital in Salt Lake, who were part of the original group from Warren's group, led by Alan Morris, got drawn back out of the woods by the Italian mafia. It was a little hit job by Luciano Gattinoni and Antonio Pezzenti, who very correctly noticed that ARDS was killing you because of the disease and the treatment. Modern ventilation was trashing lungs. And so they said, you know, we started putting people on ECMO so we could rest the lungs. And a lot of them survived. And then compared to historical controls, they appear to be doing much better. And Alan Morris went, enough of the historical controls already. We need a randomized trial where everything is carefully protocolized to isolate the effect of ECMO, in this instance of ECOR. And did a single center study, 40 patients, and they totally looked to protocolize all the care. 86% of the care decisions were following instructions. And this was the answer. Now, in this instance, I won't use my pointer because there's 3 different screens, but the top line is actually the control arm. If anything, the control arm was looking better. The good news is both arms looked a lot better than the Zapol experience from a decade earlier. And they ended up saying, hey, I think we found the intervention, and the intervention is to protocolize instructions. Protocolized care is the way to go, far better survival. No need for ECMO, and actually, this notion of getting down to protocolize and controlling individual instructions ran from this trial right into the back room for the beginning of ARDSNet and the beginning of the low tidal volume ARMA trial. And so it ended up having this massive knock-on effect into modern ARDS care. But at the same time, there was definitely a backlash. And the backlash was the beginning of protocolized instructions versus the expert opinion of the master. Elegantly described by Antonio Pezzenti from the audience in a room of about 2,000 people to Alan Morris, when he suggested that reducing ECMO to a series of instructions like a recipe would be like handing a recipe for souffle to 2 different chefs. One might be his mother, who he felt made fantastic souffle, and the other might be his wife, who he said is very beautiful, but her souffle. And he said, maybe ECMO is a little bit like a souffle. But Alan won the day, because despite an elegant and not necessarily incorrect argument from Milan, still no one was doing ECMO in adults. And another 15 years go by, which, by the way, if it turns out that ECMO was beneficial, that's a lot of people with ARDS who were denied the right care. Then the Brits got involved. You can maybe tell from my accent that those are my people. It's not been our century. Last century hasn't really been our century either. But when the Brits get involved, we still like to arrive with a certain amount of panache. And the Caesar trial definitely had that. No one had seen a trial like this before. Instead of recruiting patients in ECMO centers and randomizing them to ECMO or not, they went to the outlying hospitals. In the end, they ended up recruiting from 68 separate hospitals where patients were getting sick, and they flipped a coin about whether they should send them to the ECMO center or stay and care for them locally. They also did a bigger trial than anyone else. We're now up to 180 patients, and they randomized half to be sent to the ECMO center, where, by the way, by the time they got to the ECMO center, not everyone actually even went on ECMO. Only 3/4 of them went on ECMO. But here's the Kaplan-Meier. Wow. Now ECMO's on top with a p-value that is less than 0.05 for mortality or for survival, and for the primary outcome of avoiding death or disability also hit their primary endpoint with a p-value of less than 0.05. Wow, ECMO works, who knew? Or, as it went down in journal clubs all over the world, referral to an ECMO center works. We all know that there's lots of things in ARDS care that people don't do properly, and maybe ECMO centers are just better at doing all the other things, like low tidal volumes, et cetera, et cetera. Or maybe it's just Glenfield Hospital. I don't know if Giles Peake is at the meeting. Maybe he's just like the world's best doctor, and we sent everyone to him, and he just took better care than everyone else. Or, oops, never mind, here comes H1N1, grab that ECMO machine, we're gonna need it. And that was the beginning of the upswing, which is interesting because it was a slightly debated trial, 2 negative trials, but now suddenly everyone was doing ECMO. And that left a few people feeling we still haven't settled the issue. And I do know Alain is in the audience. Alain Combe led the EOLIA trial with a whole consortium of people. Several people are in the room, and this was designed to nail the question. And it was basically a big modern version of the ZAPOL trial. It ran at ECMO centers. We're now up to 249 patients, huge by adult ECMO trial standards, but powered to find a 20% relative risk reduction mortality. Wow, that means it can't be that big a trial. By critical care standards, it's not very big. And ECMO looks like it's on top. That's good news, but the p-value is greater than 0.07, such that when this trial ran in the New England Journal of Medicine, 2 editorials were written by 4 Harvard professors. One of them said, ECMO is not superior. And the other one said, I think ECMO is superior. Okay, very helpful. So Ewan Gallagher did this lovely piece, which I could have made lots of slides on this. I love this paper, but I'm just going to show one. He tried to do a sort of post hoc Bayesian analysis to try to understand where people stood with the EOLIA trial. And this is a slightly complicated graph, but basically saying, let's imagine across the x-axis, we're varying how much we believe in just the trial or the trial plus all the other prior trials. And the lines vertically are your confidence level around certain kinds of effect sizes. And that tealy blue line is the EOLIA trial, and everything from there or down is what EOLIA could have found. And basically, EOLIA wasn't really in a position to make any kind of statement with confidence that there was an effect of that size. That's why it's only 60, 70% or less. But the top line is just saying, how probable is it that ECMO at least helps? It doesn't necessarily massively help, but it definitely helps. And the answer is highly, highly probable. So the trial was technically negative, but probably underpowered. And at this point, it looks like it's probably highly likely that there's some effect. It's just that it might be quite small. Luciano Gattinoni called this the wheel and woe of ECMO for ARDS. I don't get this. Peter Safar speaks in Latin, and then the Italians speak in like old English phrases. So I didn't even know what wheel and woe meant. But wheel and woe is what you think it is, or maybe you all know. It's sort of just the ups and downs of ECMO for ARDS. Probably works, don't know how big the benefit. And it is not enough to get FDA approval. If this were a drug, this would not be approved. And yet, here we are. ARDS is the #1 indication for ECMO. And so now what are we doing to work out whether ECMO? Well, what we're not doing, apparently, are more trials. I did a search this week on clinicaltrials.gov, and there are 26 interventional trials recruiting or about to start recruiting in ECMO. But only 3 of them are testing ECMO. All the others are testing things about ECMO, like while on ECMO, how would you give the heparin? The 3 that are include 2 little feasibility studies that I'm not sure if they're actually going to happen. And then it looks like Dan and Ewan Goliker and a bunch of other people are trying to get funded on some platform trial. I don't know if they've got the funds yet, but they're going to look at lower risk ARDS patients and randomize them to ultra low ventilation plus ECMO, which I think is very interesting, but I don't know if it's funded. So practically speaking, how can we find out if ECMO is working for ARDS, and if so, for whom, and how do we provide the services efficiently? And this brings me back to thinking about the whole issue. So if we're trying to measure ECMO effectiveness, I'm going to suggest that step 1 is we need to establish broader data capture. ELSO and other registries capture incredible detail on the patients that get ECMO. That's the numerator. We need to capture data on people who might have got ECMO but didn't, the denominator. And the requirements are that we need to identify and or create data capture surveillance systems that allow identification and delineation of who is getting sick where, ideally at the regional level. The most obvious data surveillance systems might be, for example, ELSO partnering with folks like the ICNARC ICU registry in the UK or ANZIX. I'm not saying ELSO has to build this on their own, but I absolutely think there needs to be some investment of trying to link up with someone that is measuring critical illness at the physiologic level, bouncing up at the region, within regions. In the United States, you would think that you could do it through EHR-based collaboratives, but that would be in a perfect world, and we can't get 2 EHRs to talk to each other. Once you have the data system in place, then you just need to choose an instrument for measuring effectiveness. And it doesn't need to be an Eolia or a Zapol RCT. There are about 5 different designs that you could use that range from simplest to hardest, not from weakest to strongest, just from simplest to hardest. And the first 4 are all enabled by a region-wide data surveillance system. The last one is a classic, like a repeat of the Eolia trial. That would just be like a standard RCT infrastructure. And just to speak briefly, the first one, diff and diff, difference and difference. All you need are the following assumptions. ECMO is not fully deployed everywhere in all regions in your data system. Different regions are making changes in the amount of ECMO support they have over time, which could be anything. These changes are occurring at different times, and you have a list of what those changes are. If you can meet these 4 conditions, you can do a retrospective difference in difference design of the causal impact of the per unit change of ECMO on community at-risk populations. And this is actually what economists, not just in healthcare, but in all areas use for measuring the causal effect of policies, not just associations, and it happens in critical care. Avery Nathans used a diff and diff to look at the effect of trauma systems. Jeremy Kahn used a diff and diff to look at the effect of the sepsis mandates in New York. You could go one step further. If you could get multiple regions prepared to roll out something in the future, and you could negotiate with them about when, then you could do some type of batch random rollout. This is an extension of a step wedge design, but people could even choose when they're ready to be randomized. So in other words, it's quite leaning towards the practicalities of healthcare system delivery. And step wedge and batch step wedge are just forms of clusters. And these 2, we do them all the time in critical care. This is just a little potpourri of recent cluster RCTs in the New England or JAMA or Lancet. High-profile papers using cluster designs across all aspects of critical illness. The third thing you could do would be a lottery. If we think we're having another pandemic and there's not enough ECMO, consider people having to draw lots on who gets the ECMO among those who are eligible. It could even be weighted lots for issues of equity. We wrote about this, Doug White and I, and actually deployed in Western Pennsylvania a random lottery on remdesivir and on monoclonal antibodies. Josh Angus uses this a lot. And Josh Angus, you might know, he's over at MIT. He just won the Nobel Prize in economics. There's legacy to this approach. And if you're still looking for more legacy, it's what drove the first ever RCT. The first ever RCT of streptomycin in Britain was because Britain didn't get enough streptomycin for all the open TB. And so they basically did a lottery because there was a scarce supply of streptomycin. We could repeat Caesar. I like Caesar. I think it's a great trial. If I were doing it again, if you had real-time activation in the surveillance system, you could actually nest the trial in the surveillance system. And the only big change I would do to the design is have patients go to more than one ECMO center. And then, of course, you could just do another Aeolia or another COMSA. People are tired of these because it just about kills them to do those trials. I would point out, it's not because the patients don't want it. I went back and looked at all the trials that had been done, and as best I could tell, patients and our families very rarely refused. Now, the clinicians might not have equipoise, in which case there are things you could do to mitigate. Like in the control arm, it could really just be more like early versus late ECMO, or things that have been used for testing dialysis. There are ways of mitigating the design that might appease people's sense of equipoise. I am standing up here basically saying to all of you who collect an unbelievable amount of data on each ECMO patient that I really want you to start collecting data on patients that didn't get ECMO. So as I wrap this talk, I do want to just have a closing slide on why I think this would be a good idea. If you have system-wide data surveillance on emerging acute respiratory failure, you really understand the epidemiology. You facilitate timely triage and referral to ECMO centers, so you won't get calls about patients you think, this patient's been ventilated for a week and you're calling me now. You can support resource planning on how many units you would need per million covered lives, support multiple quality improvement and learning health system study designs, not just the ones I just quickly reviewed for studying ECMO effectiveness, but things like volume outcome relationships for the size of ECMO programs, or for testing tweaks to the ECMO program and things you do inside the ECMO program. So in conclusion, ECMO technology, wow, it has undergone incredible improvement over the last 50 years. ARDS care has also, the non-ECMO parts of ARDS has undergone incredible improvement in the last 50 years. Measuring at any moment in time the incremental value of ECMO over everything else for ARDS care has been elusive. Neither ECMO nor high-end ARDS care is available to all. And given that, asking whether the ECMO device improves outcome, I'm not sure that's the right question. Determining how to ensure optimal triage of sick ARDS patients to high-end ARDS care teams, which could be ECMO-capable teams, feels much more important. That feels like the big picture question. And furthermore, the data system and the infrastructure required to answer that question also facilitates all the other questions, like the marginal benefit of ECMO, getting the details right. And so maybe 15 years from now, we could come back and say, thanks to ELSO and other international ECMO community partnerships, ARDS care is now fully regionalized with highly effective triage systems. Regions participate in a learning network that generates rapid knowledge with robust causal inference regarding ARDS care modifications, including whether and when to deploy extracorporeal support. And with that, thank you very much.
All right, well, we're ready to get started with the next session. So thanks very much for the keynote, phenomenal lecture, and I enjoyed the Latin reminders from grade school. So my name is Navin Kapur, and I'll be co-moderating this session with Susanna Price. So thanks, Susanna, for joining me. And this is the session called Science at the Cutting Edge, ECLS and Beyond. So Susanna, if you want to do the first introduction.
So it's a great pleasure to be here. It's fantastic to see people face to face. It's not going to be Don Hill speaking to you as a first presenter, I'm afraid. We've got a substitute in the name of Bob Bartlett. So Bob, the floor is yours.
Hello to all, and let me also say how great it is to see all of us in the same room meeting in person once again, as we've done over the years. Thank you, Derek, for a marvelous, very thorough literature review and a glance forward. I will just talk a minute about looking back several years, which is what Don Hill was going to talk to us about. And Derek outlined the elegant review of ARDS trials, and of course, as you all know, during that same time, the neonatal and pediatric trials unequivocally proved that it was of value, so it became standard practice for many years. And much of that is based on the very first neonatal ECMO patient. It was in 1975. Many of you know her because you've read the paper called Esperanza, and I'm pleased to tell you that she's here today to say hello. Esperanza. A dear friend of 48 years, amazing. Don Hill was going to be here, and he was going to tell you about the very first adult ECMO case. Happened to be an ARDS case. We were not called that at the time, but now we know it is. And unfortunately, he was really wanted to be here. He was very excited about this because this year is the 50th anniversary of the publication of that patient, a single case report which led to development of ECMO for ARDS, and you've heard how that played out over the next 50 years over time, that we're still working on it. A couple of days ago, Don called me and said, I can't come, I'm really sick. He's in San Francisco, I don't feel safe in getting on an airplane. So sadly, I'm going to give his talk, which he'd prepared very nicely. However, his wife and his two sons, his sons are students at Boston University. They're right here. So I would like to introduce Jing Hill. Where is she? There we go. Don's wife and his two twin boys, Ping and Ming Hill. Please say it. So a bit of a look back. So I'm just going to present what Don had prepared with just a few minor comments along the way. So we invited him here to talk about the 50th anniversary of this really important publication, which was published in the New England Journal in 1972. The case was in 1971. Worked good. So he began with a discussion about cardiac surgery. Few people in the audience will remember this, let alone be around then, but the first case on cardiopulmonary bypass was done by John Gibbon in 1953, and a very few surgeons around the world shown here thought we need to learn about this and learn how to do it. Not many places doing cardiac surgery, but of course you know how it's grown over time. And one of those centers was California Pacific Medical Center. It was at the time the headquarters of Stanford Medical School, which subsequently moved south a while, but it was the cardiac surgery program was headed by Frank Gerbode, who you see here, working with a cardiologist, John Osborne, and they recruited an engineer named Maury Bramson, assigned him the job of building a membrane oxygenator, because in the 60s, most of us knew that the heart-lung machine was a lethal instrument if you used it for more than an hour. But we thought if you could just replace the lung part of it, which is raw oxygen exposed to blood, it might work longer than that. So they got working on this in a few centers around the country, and this is Don's description of this, but it's exactly right. Meanwhile, in the 1960s, in basement labs, in some hospitals and some institutions, a few very young, intrepid people were working on the idea of extending cardiopulmonary bypass for more than an hour. The idea is if you could get to 3 or 4 hours or a day, wouldn't that be great? And they're literally all shown here. Warren Zapol, you already heard about, working with Ted Colabo, Phil Drinker and I working here in Boston, Maury Ramson and Don Hill in San Francisco, Arnie Landay at Minneapolis at the time, and Pierre Galetti, a wonderful guy at Brown University, and Converse Pierce. So what I'm going to tell you spun out of these few people who had this idea in the 60s. Now cut to a single case. I loved hearing about the case that made you think, okay, this guy was dead, now he's alive, I'm an ECMO believer, now I got to figure it out. So this is a patient who was a young man, 24 years old, motor vehicle accident in Santa Barbara, California. And when he arrives in the hospital, he's alert and awake, he's in a lot of pain, he's hypotensive, hypovolemic, bleeding, and so on and so forth. And as you might imagine, he had a lot of injuries, a lot of fractures, pelvic fractures, leg fractures, but most importantly, a contained rupture of his proximal thoracic aorta. Nowadays, we might handle this differently, but at the time, you operated on that patient with the hope that it wouldn't rupture and they would exsanguinate on the spot. So that's what the surgeon did. The surgeon was a guy named Tom O'Brien, who, as Don says, never gets the appropriate credit for this. So he's a good surgeon. And he's at Santa Barbara Cottage Hospital. Sounds diminutive, and it is, a little community hospital in Santa Barbara. And Tom was a great guy, and he was taking care of this patient and took care of him remarkably well, but he's getting sicker and sicker. Look at, here's his x-ray, but here's day 4. His PO2's 45 millimeters of mercury. He's on 100% oxygen. He's on 5 a PEEP. That was new stuff, even trying PEEP. And his peak airway pressure is 60. And with any luck, you could modify your ventilator to get pressure up to 80. That was the idea. Ought to be good. But limping along. 4 days into it, he's making no headway. On day 5, he's even worse. His PO2 is 30. He's on 8 a PEEP. Oh my God. And he's clearly, and he's dying. So what happened on day 5 was Tom O'Brien, as it turns out, was a resident buddy of mine. We were residents together at the Children's Hospital in Boston in the mid-60s, and he knew that Phil Drinker and I were working on a membrane oxygenator, and we had shown that you could put an animal on for 5 days way back then. So we kept working on this. So we were about 100 miles away in Irvine, California. So Tom called me up and said, "Are you guys ready to try that machine yet?" And I said, "No, we're almost ready, but not quite." But Don Hill is a friend. He's done about 6 cases. He's 100 miles away in San Francisco. Let's give him a call. So we did. And then that led to the day 6 VA ECMO institution. Don and Maury Bramson came down to Santa Barbara and set up Bramson's oxygenator, which I'll show you in a minute, and put this patient on femoral VA bypass. And nowadays you're saying, why didn't they use VV? We didn't know about it, so it was all VA. And put this patient on. My partner, Angus, and I drove up from Irvine, and we spent the next couple of days looking at this patient and this phenomenon that we've been dreaming about. And this is, in fact, Don tells me it's the only photograph of this particular case. I took this picture, so it tells you the timing. But here's the patient, but here's a Bramson membrane oxygenator. You can see it took about 6 hours to assemble a sheet of membrane and a spacer and a sheet of membrane and a spacer, and it leaked and it didn't work, but it worked well enough to provide adequate gas exchange, especially on VA support. So that went on for about 3 days. Patient recovered, got better, and ultimately survived. And here is data. He was confused, then he woke up. He was in the hospital for quite a long time, cleared that up, and eventually went home. And a year later, he had good pulmonary function, and the rest of his parameters were normal. So that was the first successful ECMO patient. This is the first one ever, mind you. So we all thought that was important. So we encouraged Don to write it up, and he did. He wrote it up and published it. This is the Pacific Medical Center team, by the way, Frank Bergotti, who was running it, John Osborne, Don, and Maury Bramson, and Don what he would be telling you at this point is all about the team phenomenon. You get the right people together, doing things together, thinking together, and that's what makes anything complicated work, including ECMO. So this case was published in the New England Journal in 1972, and it's an elegant paper. You should read it. It's fun to read all these details, especially now, looking back as to what was done at that time. Not a lot different from what you're all doing every day. And Don asked me to tell you, he'll send you this paper if you call him on email. There's his number, but you can also find it in PubMed. You don't have to bother Don, but it's a great paper. So what he wanted us all to learn was, it's a single case. It was what was called shock lung at the time. And here's a patient who looked like he was dying of it and recovered. And thanks to all of you for joining in this celebration. So thanks to Don, thanks to the family, thanks very much.
Great, thanks for that. That was a phenomenal case, and seeing that oxygenator, certainly humbling to see where we are today. So the next speaker is Roberto Lorusso, who's a full professor of cardiac surgery and ECLS, coming from Maastricht University Medical Center, Cardiovascular Research Institute in Maastricht. So Roberto.
Thank you. Thank you all. This is a really great honor and privilege for me being here with all these friends and colleagues. So thanks to ELSO for this invitation. So these are my disclosures. So anytime I'm being invited to give some kind of these lectures, I want to always pay a personal tribute. And I hope you know this guy because you are all using his technique. And I think this guy really deserves a lot of recognition. And as you know, Seldinger is our really daily practice. And I think he should have really deserved a Nobel Prize for that, because it's not only in cardiology or surgery or whatever. But I think we really need, again, to pay a tribute to another guy that you all know very well. And I think also this guy really would deserve a Nobel Prize, I think, for all the patients who really were treated and survived. And I think that we really need to pay a tribute to Bob. So, having said that, when I started my career, as you can see from my few hairs and why the ECLS statement was, well, ECLS is just put into cannula and then pray. That was a statement. I was trained this way. Well, I think it's a little bit different nowadays. These are the new perspectives. I don't want you to go through because I'm going to present really each one of them, and you will find all these in the new Red Book. And I would like to really thank all the contributors, particularly Graham and McLaren, for his leadership in this very, very fantastic adventure. So I really want to tell you that this is a new adventure. So this is really a new era for ECLS in the future. And this is the telescope from NASA, and we now see the universe in a different way. And I think nowadays, this era is the time for new perspective also for ECLS. So what is now the time for what, I would say? Well, why we need more ECLS? Why we need to do something more? Well, I show you something. This was the year 2000. Look, the GASTO trial, the most important trial on cardiogenic shock. And the results were quite disappointing. And the editor-in-chief of the European Heart Journal, you see, said a more cardiogenic shock, a more aggressive approach is warranted. Year 2000, 22 years ago. Well, let's see about this other study, big study. This was 2012. Well, again, you can see fatality rate very high, 60%. And the conclusion was, again, look, we are disappointed. We should do more. We should be more aggressive. Well, I think that now the latest data in 2018 show clearly the cardiogenic shock is going up and up and up. But look at the, amount of mechanical circulatory support, which is at the bottom line. There's no change. There's no change. And this is also another study showing the temporal trend and the use of mechanical circulatory support in cardiogenic shock. And look at the mortality and look at the use of MCS. Nothing changed during, well, this is 2017. But I think this is really something which warrants a change in action. And this is a new, very recent paper, again, discussing the new concept, the new development in the cardiogenic shock. And I think we have to bear in mind a few items, few really points, very important points. We are going to treat more and more complex patients, more elderly patients, emergency cases, a lot of comorbidities, and we need to have a multidisciplinary team for that. And we have more transcatheter procedure, but this means that we are going to treat a lot of inoperable patients, and I think we are going to expand indications. We have Susanna Price here, and this is part of also her work. The European Society of Cardiology is moving very much into this. And this is just to give you an example how the topic is very important for the European Society of Cardiology, and handbook, and also new expert consensus guidelines. So this means that finally something is moving in the cardiological and, I think, cardiosurgery communities. And I think this is a new classification of acute heart failure. You can see it's no more in a NIA class or whatever, but it's about the SCAI classification, and you can clearly see that the ECLS could really find its role in this new classification. But what is important is timing. This is an editorial and gives you exactly the concept that we have really to run and really do that in a timely way. And I think I like very much this editorial because it gives you an idea. We all know. I mean, you have to treat the patient in the right place, with the right time, with the right tool. And I think we are really lucky that we have these tools. So we wrote this interim guidelines, and you can find why this is going to be really important, because the indications are expanding. So the ECLS application is going to be important in many settings. And what about post-cardiotomy? I'm a cardiac surgeon, and this is quite the bad news part. And I think that the results are quite still disappointing. But why? Because the cardiac surgery patient is an even more complex patient. It's really a patient of its own. So a lot of bad things, a lot of comorbidities, a lot of myocardial injury, and so forth. And we recently made this expert consensus paper. Really, it was a fantastic job with the Force Society, and I think this is also something like an effort towards at least an effort to improve the results, which are still disappointing. And soon you will find an ELSO monograph on this topic, and I really suggest this to all of you, at least for the ones involved in cardiac surgery. But look at the trends in cardiac surgery. Really nice paper with Vala Bayosula, more than 130,000 admissions for post-cardiotomy shock. And more than 50% of these patients require mechanical circulatory support. But look at the trend. Again, the cases are rising, but the use of mechanical circulatory support still stable, no increase in the latest years. And if you look at the two graphs that I showed you before, cardiogenic shock and post-cardiotomy shock, they are the same. So again, we need an action even in this setting. And I like very much, Jonathan is here, I like so much this editorial because we really need to implant the ECLS in the due time, in the timely fashion. And the importance of shock team now is getting more and more important. This is a very nice paper about the Detroit Cardiogenic Shock Initiative. It is clear that once you establish a structure, let's say, approach to the problem, the results are much better. And this is going to be a very, very important topic for the future, and particularly with the use of temporary mechanical circulatory support in these patients. And then we have the bad part. We know complications, but also the technology. This comes again from the paper of the European Society of Cardiology, and we all know these figures. We all know that the more the ECLS is in place, the more the patient is exposed to the risk of complications. But I think we have now a new era. We have new cannulas, we have new pumps, we have new oxygenators coming to the market. We have new devices, and particularly the combination of devices like extracorporeal support and transaortic device. We have maybe also new drugs and new management. We have integration between treatment and diagnostic. This will be another very important aspect in the future because we have a machine in contact with the blood flow. We need to have more information from the patient. And I think we have really to make improvement in monitoring these patients. So new configuration and management. I think in the future, the famous statement at the beginning, 2 cannulas and then pray, is completely changing. We have now hybrid ECMO, and we are going to handle something that in the past, it was really a sort of nightmare for a lot of people, so right ventricular failure. We have now a lot of possibility. Pulmonary artery cannulation gives us a lot of new options and new hopes. And you can see now between cannulas and devices, we can really treat the patient in a direct way, in a, let's say, etiology and disease-directed management. So a lot of improvement. And also the way we are dealing with the patient for the future. Is a transition going to be needed? Well, you know you can use different configuration because the patient can go from ECLS to more durable devices. And I think this was a very nice paper recently about the transition and the predictors for this successful transition or bridge to more durable devices. So again, in this will be a lot of new development. And also the way we are dealing with the ECLS configuration and the use of Hoffman clamp to adjust the flow to more complex, again, ECLS configuration. Again, all these things are changing. There are no more 2 cannulas, but there are more patient-directed management. And I think another very important aspect is awake patient. This is CASIA, and I think this is going to be more and more used in the future. In the past, it was quite a sort of a nightmare, awakening a patient in the VA ECMO. Now it's really a reality. And the research, this is also very important. We have ongoing a lot of studies, randomized studies, and you know very well about the use of ECLS in cardiac arrest. And we are now also, we finished also our study in mastering the multi-center trial, and the paper now is under review. And we have also other studies in post-cardiotomy, but I think what is really important, and we have the treasure of the ELSO registry. This is going, again, for the future, giving us a lot of important information. And to go at the end of the talk, I think that this is a little bit another aspect which we know is under controversial discussion all the time. I think that this is something that is going to be more and more used in the future. I think that we have a lot of pros and cons, but at the end, I think that we know that this should be done at the very beginning of the ECMO implantation. That could be done in a non-invasive way, or we can do it with catheters, devices, cannulas, but I think this is going to be also the future for every VA ECMO patient. And we have to do more studies. These are preclinical studies we've done with a Prague group, and I think these are very important to give more knowledge about this setting. So in conclusion, I think that this was, again, going back to my beginning, to the beginning of my career, a little bit and the history. But, you know, the transition from cannulation to complication is really subtle and narrow. And I think in the past, this was a little bit the reason for some skepticism about the clinical and non-clinical community. But I think this is not true. And I think absolutely that now it's a new era. Again, we look in a different way, like the telescope of NASA in the universe. I think that now it's time to trust, not to be skeptical, not to be pessimistic, but to trust and further invest in technology. And I think that we know that we need to increase our knowledge, our training, and responsible expertise, of course. I think the next 10 years definitely will be the era of mechanical circulatory support and respiratory support, as unfortunately we tested in the last 2 years. And I think, again, research and relationship with the companies and medical and non-medical professionals will be really important for a multidisciplinary approach. And this will help the welcome to the machine, because we need really to work together. Thank you for your attention.
So thanks very much, Roberto. That was a fantastic presentation. So now it's my pleasure to introduce a great friend and colleague, the awesome Peta Alexander. She is a pediatric cardiologist. She and I had the pleasure of locking horns in a debate in Hobart, Tasmania in the pre-pandemic world. So you're going to tell us, apparently, pediatric ECMO research and trials. Thanks, Peta.
Good afternoon, everyone, and welcome. These are not my slides. This is not a pediatric talk. And so we've got two options. I don't know if we can flip the slides over. Thank you. I'm happy to wing it a little bit, but thank you for the introduction, Susanna. We did have a fantastic time in Tasmania, but it was well before the pandemic. It's not there yet, I don't think. I can start my introduction while we're waiting for the first slide to come. It's an absolute honor to be invited to be presenting this talk at the opening session of the first in-person meeting for the last few years. This is actually the end of my tenure as the co-chair of PediECMO, which is the small now pediatric network within the ELSO community. And just looking out at all of you here, it's quite remarkable how much it's grown in the last 2 years. So as I'm presenting this slide, these are my disclosures, but the unspoken is that I am presenting on behalf of an enormous community of committed clinicians, scientists, investigators, and collaborators. And many of the slides that I'll be presenting are not my own. All blame to me for the details that I get wrong, but all credit to the investigators on the slides. So as we do think about pediatric ECMO over the last couple of years, we have been blitzed by the number of adult patients that have used this therapy, and also by the number of publications that have come through for adult ECMO utilization. I was relieved, however, that there are still plenty of studies that I've got to talk about this afternoon when I looked it up on PubMed as we started the preparation. The number of studies have steadily increased for pediatric ECMO use over time, and although these don't hit the heady heights of the adult populations, there are kind of 280 to 400 studies per year. What I'm going to spend most of my time talking about today, though, are the prospective studies that are being funded by important national organisations. These are the NIH reporter studies, but there are international studies also being funded, and these are going to change the face of paediatric ECMO moving forward. Some of these studies are actually just the baseline consensus. Where do we start research in this space for the paediatric population if we want to build and do prospective studies? This is a consensus conference series that was funded by the NIH. It's not specific to ECMO, it's the taxicab study, Control and Avoidance of Bleeding in the Pediatric Population. But they actually had a subgroup specifically looking at the cardiopulmonary bypass and ECMO population. They included implementation scientists as part of this modified Delphi process to be sure that any recommendations that they moved forward could actually be incorporated into clinical practice. And that's something that we've done as we've moved forward with other consensus finding projects. This is one that I share with Dr. Mazinski, the Pediatric ECMO Anticoagulation Collaborative. And our lofty goals were to try and develop evidence-informed consensus statements for the management of anticoagulation of critically ill infants. But probably the most important part of the project has ended up being defining the research priorities as we move forward in this space and leveraging the network of people that have come together. You can see many of the subgroup chairs on the slide to be able to really move forward as a community. Neurodevelopment and neurological complications are forever on our minds with pediatric ECMO. And many of you will know Dr. Bembia, who's been moving forward with her BEAM study, the biomarkers in pediatric ECMO observational study, expecting to complete in a couple of years. More recently, Dr. Lakshmi Raman and colleagues have been funded for quantitative optical tools to continuously monitor cerebral autoregulation, including blood flow, oxygenation, and inflammation. All of these studies will be presented at some stage over the next couple of days, so you can look for them on your agenda for more information. Dr. Anne-Marie McGuigarian and the collaborators in the Canadian Critical Care Trials Network are looking at brain and ECMO outcomes as well, but this time particularly with reference to the way we manage carotid artery reconstruction at the end of ECMO runs. Many small children are still managed with VA ECMO cannulation, even sometimes for respiratory support. And the debates that happen at these meetings are often surrounding whether to reconstruct or to ligate those vessels. Hopefully these studies will start to inform. Dr. Bhargava has already been mentioned many times today, but he's established a prospective observational study, the ASCEND trial, looking at ARDS in children and ECMO initiation strategies and the impact on neurodevelopment. This is a really innovative study that is seated alongside an interventional mechanical ventilation study, the PROSPECT study, with data collected within the ELSO registry. So he's leveraging all of his many strengths to get this done. Despite the pandemic, he's continued with study enrollment with more than 105 children enrolled from 90 sites from all over the world, with a study expected completion date with 500 patients by 2026. I should have mentioned that I have very few results from the pediatric ECMO research talk, but I really want to share how exciting it is to be in this space of funded studies for pediatric research. And the next 3 studies that I'm going to talk about are all actually interventional studies for the population, looking at how we can improve care. So the first is the ecstatic study. This is an ECMO hemostatic transfusions protocol looking at populations of children who are supported on ECMO anytime 0 to 18 years in any ICU and VA or VV cannulation. They're funded now for a pilot study, and the idea of that is to make sure that within this population we can actually randomize, that people are comfortable randomizing to a liberal versus a restricted platelet transfusion strategy, and to use EFIC for one of the first times in the pediatric interventional study. So there's been no previous RCTs on this in ECMO in children. They're using an adaptive trial design to try and reduce the study size required, and they're using exemption from informed consent with deferred consent within the first 24 hours. And so we're really watching this within the pediatric community. 5 centres are signed up, and we're expecting 50 patients to be enrolled. The second prospective interventional study in pediatric ECMO that's been funded as we stand here is the Hydrogen Fast study. Dr. John Keir and Lynn Sleeper have been funded by the NIH for a feasibility study to look at hydrogen gas piped through the ECMO circuit in order to reduce neurological and renal injury post cardiopulmonary arrest. This will be mainly a pediatric cardiac population enrolled, and only at 2 centres, Texas Children's and Boston Children's Hospital for a start. But having done the translational science work and proven safety in adults with the gas, they've now been funded, oh, I'm sorry about that, for a randomized controlled trial of using this innovative therapy. At the same time, this is a picture from yesterday, which was our kickoff meeting for the investigators of the TIDA trial, which is a Department of Defense study of transfusion practices in pediatrics. So this is the trial of indication-based transfusion of red cells in ECMO. Dr. Ravi Thiagarajan has been working on this trial for a number of years, and when pairing with Dr. Jane Newberger and Dr. Lynn Sleeper, they've got the perfect team together. You can see many of us there as either site PIs or on the clinical coordinating team or data coordinating center, and we're really excited to launch it yesterday. The innovation within this interventional study is basically that the transfusion strategy as the interventional arm is not just a threshold. It's an indication-based arm, and patients are transfused for bleeding, for inadequate oxygen delivery to tissues, or otherwise until they reach a much lower threshold than we would usually be comfortable with in children. There's also an innovative trial endpoint with the P-SOFA score looking at markers of organ dysfunction before ECMO and whether or not patients recover that function during the ECMO run. It means that we'll be able to get complete capture of data by the time patients leave hospital, but we also have a primary neurodevelopmental follow-up endpoint at 12 months to make sure we're not missing negative consequences. So with so much largesse and so much excitement in the pediatric community at the moment, there's also complications of so many interventional trials being funded at the same time. We're still a small population. We're all looking at randomizing between 50 and 228 patients over the course of the time point, but most centers still don't have a lot of patients that meet criteria. And as such, we're at risk of missing the opportunity to include patients in trials or not co-enrolling trials because there's concern for negative consequences for each of the studies. Against that background, the Centers of Excellence in Regulatory Science and Innovation, the FDA CERSI collaborations, specifically the collaboration at UCSF Stanford, have piloted a modified Delphi process where we looked at what a framework for an adaptive platform trial would look like in the pediatric ECMO population. To be completely transparent, this is a mainly pediatric cardiac population with collaborators with the FDA as well as well-known established trialists and some patient representatives and perfusionists. But we looked at the pediatric ECMO population to see what meaningful questions we thought would be worth answering if we could stack them up together. This is the start of a framework that we're still brainstorming through. You can see that unlike many of the individual randomized control trials, what we're thinking about is that in an adaptive platform study, we'd be able to include all ECMO patients, any ECMO patients that meet the pediatric criteria. And for the FDA, that's less than 21 years. Clearly, there'd need to be stratification around risk factors for poor outcome. So we've considered respiratory versus cardiac or cardiopulmonary bypass, post-cardiopulmonary bypass patients, and elective cannulation versus cannulation that occurs during CPR. You can also see that we'd brainstormed a few different domains of potential therapeutic strategies, including anticoagulation, red cell transfusion strategies, and sedation. But we'd also like to collect data on ECMO circuit components that are used, in the same way that we find that that's so important within the ELSO registry. We'd expect a global endpoint for all of the arms to be the functional status score or some construct of the functional status score, because that's a meaningful patient-centered outcome. And we'd expect that as we received results from the early parts of the study, that the platform would adapt with adjustments to randomization ratio. A stable platform trial would both allow new questions to be asked of the same population without the build and rebuild of each individual randomized control trial, but it would also mean that patients can contribute to answering multiple questions with the same ECMO run. And with all of that being said, PD ECMO is on this evening at the ELSO meeting, and this is the end of my co-chairship with Dr. Todd Kilbar, who I'm sure is here, and we'll announce the new co-chairs this evening at the PD ECMO meeting if any of you would like to join us, and you'll be able to hear a lot more detail about all of the studies that we've discussed. Thank you so much.
Great, thanks for that terrific lecture. So my pleasure now to introduce Dr. Bart Griffith. He's the Thomas and Alice Maria Hales Distinguished Professor of Transplant Surgery from University of Maryland, Baltimore campus. Welcome.
Does anybody need to get up and stretch? It's been a long run, and it's been a delightful one. I wanted to thank the organizers for inviting me, and particularly for the master, who I have followed now for more than 44 years, and I learn something every time he speaks. Thank you, Bob, for being Bob. My topic today is a little off-kilter, but it is about pushing boundaries, and I think it's about not vain excesses in terms of celebratory dances for what will be a long haul. I'm going to try and tell a very long story in 10 minutes. So if you were to begin a program and want to start thinking about animal parts for humans, and you sewed a pig heart, which looks a little bit like a human heart, actually a lot like a human heart anatomically, into an abdomen of a baboon, and expected that to work, you would end up with a picture that is shown on the right side of this slide, which is basically a heart that becomes necrotic in about 20 minutes. It does so because it undergoes acute rejection, which is, in the early moments, really about thrombosis. It's about poor control of coagulation, recognition of a xenoantigen, antibody recognition, complement activation, infarct, black organ. So how in the world do we go from this to considering an animal heart or an animal lung or an animal pancreas or other animal organs for humans? And it's through the marvels, really, of genetic engineering. And let's see the forward mark. How do we go forward here, kids? There. Okay. So the animal's heart that I placed into David Bennett a while ago had 10 genetic edits. There were 4 edits in which carbohydrate moieties on the surface of the endothelium were removed. A growth hormone kind of producing gene was removed, and then there were additional added genes which help to control the coagulation system, which is off kilter relative to humans, and also an anti-inflammatory gene was added. This all started in our laboratories about 6 years ago when Mohammed Mohideen joined us. He was working tirelessly in the field of xenotransplantation, and rather anonymously, I might add, at the NIH. His big breakthrough was really his ability to maintain a pig's heart in a baboon's abdomen for more than 3 years. And he did that with the hookup as shown here. And this, those of you who understand this work knows that this is a live heart, but it's not a working heart. It's being perfused by the abdominal aorta, and it's draining basically its venous effluent into the IVC. But it's a good traditional way to look at immune suppression, and it's very commonly done in rats for the development of new drugs. It was also used in Mohideen's laboratory to test different immune suppressive aspects along with additions of gene edits. So the drug that seemed to make the big difference was an anti-CD40, which controls B-cell rejection. Now, most of us in the transplant world for allotransplant know it's really all about the T-cell regulation. Well, you flip the switch for xenotransplantation because it appears to be more of an antibody-mediated problem than a T-cell one. So if you don't control the antibodies, you're going to have trouble. So just like cyclosporin and tacrolimus controls T-cell activation, the anti-CD40 is a great drug, never before we used it, used in a human, but it seemed to work well in these baboon implants. So what does that look like? So this is the picture of an animal that has a beating pig heart. This is a baboon's shaved stomach. You can see it kind of pulsating there. That's what it looks like. You go and you make rounds on your patient and you feel the abdomen. If it's beating, you figure, okay, it's not rejected. So that went on for 784 days in this particular animal at the time of this picture. This animal was permitted to go more than 3 years, and then the decision was made, well, what would happen if we stopped that anti-CD40? Because we have a genetically altered heart, maybe we won't need immune suppression in a classic sense. The anti-CD40 was stopped, and within 3 weeks, they lost the heart. So 3 years, stopped it, 3 weeks later, it was gone. So it obviously was still working its magic on the xeno protection. And this is what it looks like now in our laboratory on the left. It was important to demonstrate that not only could you do an implant in the abdomen, but very important if you could translate that into a human-type transplant where you would remove the baboon's heart, implant the pig's heart, as has been done in this picture, into the baboon, and see whether or not it would provide life-sustaining function for a longer period of time, 6 months to a year. Well, it's shown here coming off bypass, firing away. It looks like any other transplanted heart. Really, you couldn't tell whether this was a pig heart or not. The anatomy is pretty close. And this is a 23-kilogram baboon, and it's received a 20-kilogram pig heart. You can see on the right, this is our ICU, if you wish, for the baboons, and this animal required a lot of medication, not exactly an outstanding success, and this animal passed away at 48 hours. In fact, we were almost out of business, and it reminds me of lots of the hard work early on that most of us have seen. We've seen actually more heartache than heartwhelming outcomes in our laboratories, but that's what has driven us. The translation to orthotopic life-sustaining heart was tough. We had between I guess it was a total of 16 cases between 11/17 and 8/19, and it's about $750,000 a case. When you add up the cost of the genetically engineered animal and the baboons and the animal care, and of course the big surgeon's fee, it comes up to about $12.7 million for those 16 cases, and only 3 lived more than 2 days. Well, our sponsor, which was United Therapeutics, was getting a little nervous. They felt that perhaps we weren't the right bet. About the same time, a letter was published by our German colleagues, and Bruno Reichart, known to a lot of our European investigators that are here today, but worldwide in xenotransplantation and allotransplantation. That team in Munich was able to put the pedal to the metal and get animals to survive. And this demonstrated a number of animals that had made 3 months. Well, to us in Maryland, when this came out, this was a miracle. It made us feel kind of meek because we couldn't do it, but we found out what their secret sauce was. And it was all about the use of a non-ischemic preservation method for these pig hearts called ex vivo. Basically, we had tried to duplicate how we take care of human hearts. We take them out carefully, we put them in ice, and we transplant them as quickly as we can. That didn't seem to work for us, didn't work for the Germans, and it wasn't until they switched over to a non-ischemic preservation system using an ex vivo perfusion system were they able to convert the situation into better outcomes, as did we learn to do. We jumped on a plane, got to Sweden pretty quickly, and went to ELSO, which is where Dr. Stig Steen has done his work and has demonstrated, that his device could be useful to the Germans. This is a picture of basically a pig heart, genetically engineered, that's being dropped into the ex vivo system that's not easy to see, but there's that well, and it's covered up with a sterile dressing. But this, in fact, is a rather historic picture because this was the picture of the pig heart that went into David Bennett. And this is the team removing the pig heart. And that happens to be a postdoc, an MD postdoc, getting his PhD in xenotransplantation in our laboratory, Corbin Gorich, who's helping to do, in fact, did the explant. So anybody want to do a lot of work, come on over to Maryland. We'll put you to work, and you'll do some pretty important stuff. We had a patient that could not wean from ECMO. He'd been on ECMO for 48 days. He'd been hospitalized for 61 days flat on his back. His white blood cell count was not robust and ultimately went up and down when he saw a new antibiotic or got a new infection. It would fall. His platelet count seemed to be deficient. He had striking sarcopenia. Sarcopenia means lack of muscle. I had to learn that word. It's a good one. His left lower leg is shown there, and that's my size 7 glove hand around his lower leg. It was really tragic how disabled he was. He didn't want to die, and he said, "Is there anything you can do?" And I got the crazy idea that perhaps we had done enough in our lab with a 9-month survivor and now consistent 6-month surviving baboons without rejection, that maybe we could go ahead. We petitioned the FDA. We got it done. It was a fairly traditional operation, and you can see that this is a pretty fantastic looking heart, the way it's contracting. This, I think, was maybe on day 23, something like that. The upper part of this screen is what's called a stress echo. It shows beautiful contraction and would be the kind of allotransplantation you would dream of and don't often get early after transplantation. It was stunning, actually, that this heart was doing so well. It never saw an inotrope postoperatively. We had lots of complications, infections, low white cell counts, lots of antibiotics. He was probably on continuous antibiotics. But the heart was a rock star. It really was amazing. And everybody kept pushing us to do endomyocardial biopsy, and we were terrified. He had low platelet count. We didn't want to have bleeding. And he was doing great. Why do a biopsy? We finally did a biopsy. Our cardiologist twisted our arms. We couldn't take it anymore. This man was so sick. Derek, hi. That's Chris Wells, who came from our shop in Pittsburgh 22 years ago when I left to join us for physical therapy. But she's helping David hold his head up. He was so weak. I mean, this is almost one of the first times he had been semi-vertical. Great humanity and great empathy was shown to David, and he was treated like royalty because of what his commitment to the experiment was. The young lady behind is one of the nurses that went to our laboratory to take care of our animals in the evening after the first post-op day. So it was a nice team approach. This was the biopsy. We finally, gave in, got the biopsy. This was a 34-day biopsy. And when I saw this biopsy, and I assume some of you do heart transplantation or have talked about it, that's a biopsy that's about as normal as you can get. I didn't find one inflammatory infiltrate. None of the blood vessels looked like the endothelium was aggravated or ready to reject. I was so excited, I ran around and showed my bosses this biopsy, and I have a lot of bosses these days. It took me all afternoon to track them all down, but I was so excited, it was like, this was a tincture of youth. I mean, I felt great, this was wonderful. We have this patient, and he's not rejecting, and he has a pig's heart. Yeah, he had a pig's heart. I'd go home and tell my wife, I can't believe it. I'm sitting on the side of this man's bed and talking to him. Denny, I said, George, he's got a pig's heart. And she looked at me, she said, yeah, you put it in there. Yeah, she said, I know that. I heard it on the news. So I'm trying to show, I want to draw this to a close because I know that it's late. But this was a kind of the high point where we were so optimistic. And I show a graphic slide imported into that slide, into that biopsy, which shows a blue, a red, and a green. The green is tropomyosin, basically, troponin. That's coming out of the heart cell. That's measured in hearts. If you have a heart attack, that green line goes up because you leak that into the cells from myocyte necrosis. The blue is IgG and the red is IgM, and those are antibodies that are anti-pig antibodies. So those are measured specifically against this cloned pig. We would measure these antibodies against endothelium that we grew in the lab. So we knew exactly that these were antibodies focused on those epitopes. And so we were going in the right direction here. Everything looked good. The anti-human pig antibodies were low. They weren't going up. Biopsy looked good. And the muscle weakness or the cleansing of the heart after implant seems to be quieting down. The heart's happy. Well, didn't seem to stay that way. You can see what's happened to this wonderful nadir where after one, which is the first biopsy, you can see that green line's rising. We're leaking enzymes from the heart muscle, and that usually suggests some trauma or ischemia. We're doing echoes all along the way. It looks great. And I'm saying, forget it. Doesn't mean anything. It's probably just, I don't know what it is. And it wasn't until the blue started to get really scratchy out there around 50, and we started to see human anti-pig antibody begin to show up, both of the IgG and IgM class. At this point, about day 43, it was a Saturday morning, he looked like he was having sepsis. He looked a little clammy, his blood pressure was a little low, he didn't feel very good, and he was close to being reintubated. We measured his circulating IgG, and those in the audience that take care of critically ill people know that that's about a 10th normal. So we gave him IVIG to supplement it because we thought he was dying of an infection and wouldn't be around the next day. The problem with that decision is IVIG comes from pooled samples. And guess what we're all exposed to, and guess what all of us in the audience have? That's right, anti-pig antibodies. So we gave him a bucket full of anti-pig antibodies, which confused the interpretation of the blue and the red. Were those de novo antibodies that we had given, or were they antibodies, his own, that we didn't give, or were they antibodies that we gave to him by supplementing his IVIG? So hard to know for sure. We were in a black box, didn't really understand. And of course, all these results are coming back a week later. You can't just send it to the lab and say, what's the anti-pig human antibody count, right? They look at you like you're nuts. So we had to go to the lab and grow these things. So it took a while, but we're putting it all back together now, what was happening, in fact. So then here, we saw that he was worse. He got a little bit better after that first sepsis-like syndrome, and he was back in a chair and looked pretty good. Actually, we were talking about where we're going to rehab him, And then all of a sudden he got sick again, and we gave him pheresis now, thinking that it must be rejection, has to be rejection. We don't know what's going on. But overnight his heart thickened and maybe got 4 times as thick as it was the day before, and he went into acute diastolic heart failure, meaning his heart couldn't relax enough to fill. It was squeezing, but it couldn't fill. Well, another little thing we had been watching that I haven't told you about yet that you might know something of was the presence of a PCMV virus. PCMV is actually a herpes virus. It's in the porcine class of animals, and it's what I call a hitchhiker. It can get in an organ, hang out, just like your cold sore virus does, right? Doesn't happen, it doesn't come out until you're in a windy storm or it's cold or other things happen to you physiologically that changes your immunity, and all of a sudden you blossom with a lip ulcer. Well, it causes a deep injury when it activates, right? So it goes from being non-active to active. And you can see we can measure, and we had been measured in the blood, the presence of this DNA, free DNA of this virus. And these are spectacular assays where you can measure free DNA of any bug, you know, and we just happened to be following all of the ones we thought might affect our patient. It had bumped up a little bit, but then it went nuts. It went nuts when he got really sick, around day 50. It went really high. We were able to hammer him hard with antiviral then, but that was against a white cell count that was less than 3,000, and all the antivirals are really difficult on the bone marrow. So we were struggling all along with our bone marrow and antiviral therapy. All along, you can see we kept changing our doses of antivirals. And finally, I think we did get it under control, and you can see that the DNA molecules dropped finally after we got him on a very, very potent antiviral called aciditavir. On the left, post-op day 19 is a traditional echocardiogram where you're looking at the short axis. That's the left ventricle below, the right ventricle above. It's squeezing like the rock star that I mentioned. After he had had that first sepsis episode, the heart began to change. And you can see it looks a little different, looks a little thicker, and it's not squeezing as well. And it's undergoing this process of acute diastolic heart failure. Well, he got so sick, we put him on ECMO for the last 7 days of his life because his heart just couldn't keep up. And we thought maybe with pheresis we could reverse this process, and we hammered him with all the antivirals. His family, and that's his son, who he had been estranged to for more than 5 years before the transplant brought him together, brought the whole family together and made him very happy. They helped him make a decision to kind of let life pass, and so we pulled back on our support, and he did then pass away. I have the recording of him actually passing, but that's a little modeling for this morning. His next biopsy, day 50, before he passed, again showed no evidence of rejection. So we have a xeno heart functioning beautifully with no evidence of rejection until something, I think, very virally related happened. And the reason I think that, and here's the heart, it just blew up on us, okay? So that used to be a beautiful little heart, and I've never seen anything like this. This happened in 24 hours, and I liken it to when you turn your ankle on a curb, and your ankle swells. From the time you last looked at your ankle, it's now giant. That's what happened to this heart. This heart had an injury that affected its blood vessels and permitted a massive leak of fluid into it. And I'll put that together for you in just 1 minute. But the biopsy doesn't show any rejection. Everybody's betting rejection on this thing, right? Of course he rejected. He put a pig's heart in a patient. Well, we finally got to the source of the problem, and it wasn't easy. Again, he had had about 10 days of really high antiviral therapy, and remember that the viral DNA had dropped. We were getting ahead of it. But unfortunately, the damage had been done. There's a picture on the autopsy overlay. This is in situ hybridization picture where we're looking at a couple of viruses here that are active. And you can see viral RNA present in those pictures. And you can also notice in the picture of the one up or on the right, that's kind of the bigger one, it's sitting right in a capillary. And that's where this virus hangs out. It hangs out in the capillaries of the heart. And when it activated, it blew up the capillaries. I have wonderful EM pictures of the capillaries just lysing. And I think what happened to this man on that day 50 was he just had insufficient integrity of his capillaries, and it just caused a massive swelling of his interstitium. And finally, that swelling interfered with perfusion, and loss of capillaries interfered with perfusion, and that's how we lost the muscle cells, and that's why we lost contraction, and that's why the troponin kept coming out now. So I think it was something that we missed. I think it was something that we can prevent in the future. We're going to keep digging for the cause of death. The relative roles of iatrogenic use of IVIG, we're going to rethink that hard the next time, but we're going to avoid taking a patient as sick as this gentleman, so we maybe don't have to face that issue. PCMV is likely the cause. Acute antibody-mediated rejection, I don't think so. We have no evidence of that. We now have a better screening tool for the latent virus to exclude it from the pig in the beginning. If we don't transplant it with the heart, the patient won't get it. Donor animal care is also changing to avoid cross-infection. These animals have their children, if you wish, under cesarean section. The baby's moved to another barn that's absolutely clean, and that will be how the commercial hearts are raised. I have written to the FDA for permission to proceed with one more case and to see how that goes. There is a plan for multi-center FDA trials of xeno heart transplantation that will probably not start till 2024. And in the meantime, we're going to have to go an expanded access or compassionate use based upon our laboratory experience. I hope they'll listen to us. We've learned a ton on the first one. Dave had a chance to help. He said if he didn't make it, I'm sure we would learn a lot. That said, on Dave's entrance into the operating room that morning, he looked at me and he said, "You sure I can't get a human heart?" And I keep remembering that. He's still in my mind. Anyhow, thank you so very much, and I hope we can get back and talk to you about this later.
So thank you for an absolutely extraordinary presentation. And with this, I'm going to wrap up this amazing plenary. We've been from 50 years previously. We've looked at children, adults, hearts, lungs, humans, and not humans. Who knows what we're going to be hearing about 50 years from now when we're hearing what we were doing today. So 50 years from now, I won't be here, but some of us may be. I'd like to thank the extraordinary speakers. I get a sense that here at this meeting, we are amongst pioneers. We're amongst the people who are setting the agenda for the future, and it's completely inspirational. So thank you to the speakers, thanks to my co-chair, and I'd also actually thank the organisers of this amazing plenary session. It's been an absolute privilege to be here. Enjoy the rest of the Congress. It's going to be fantastic. Thank you.